Ice, ice, baby!
When dealing with alternating voltage, we handle and calculate with sinusoidal waveforms. Perhaps the most intuitive way of representing them is a function of time. There, the function has an amplitude, initial phase, and repeats after a period t. The frequency characterizes how often the sinusoid repeats per second and is the inverse of the period t. However, since the function repeats after one period, it can be more convenient to choose a different way to represent all relevant information about the function and skip the repetition. For this, we use the fact that in each full period the phase of the sinus function goes through a full rotation of 360 degrees, which can also be written as 2 pi. We can plot this as a phasor completing a circle in counterclockwise direction. The length of the phasor is the amplitude, and the value of the function is the sinus of the phase angle multiplied with the amplitude. It can be also read off as the y value at any point in the rotation. The angular frequency relates our phase angle to the time. In this display we have removed much of the redundancy, since after one period the phasor returns to its original position, but we need not endlessly expand our coordinate system. Complex numbers are a mathematically convenient tool to express such a phasor. Using this way of writing the phasor, the amplitude of the sinusoid turns into the magnitude of the complex number. The time-dependent phase angle stays the same. We rename our y-axis to imaginary axis and the x-axis to real axis, where we plot the imaginary and real parts of the voltage respectively. In this display, it is most intuitive to have the real part represent the actual value of the function for any given phase angle. This real part is calculated via the cosine. Sine and cosine differ only in a phase shift of 90 degrees, meaning all we do is read off any phase angles with respect to a cosine function, not a sine function as we did before. The complex representation now offers us 3 different ways of representing the same number. One is via the exponential function with magnitude and phase angle. The second involves the cosine for the real and the sine for the imaginary part. And the last is just the coordinates in the imaginary plane. Representing just the voltage, the phase phi u is time dependent as our voltage changes over time. Similarly, we can represent the current as a time dependent complex number. But the relation between two sinusoids of the same frequency is time independent, as both phasors rotate at the same speed. The relation between voltage and current, which we call impedance, is just such a relation and therefore can be represented as a time independent complex number z, with the 3 familiar forms. The real part of the impedance is called resistance, and the imaginary part the reactance of the impedance.
Alright, last time we discussed various forms of representing the information of a sinusoidal waveform. Let us expand on this concept of different ways of looking at information. This should not be a very new concept, indeed we do it every day without even noticing. Consider just the information of how to get home after work or after university. You may remember this information, for example, as a series of directions to the bus, the number of the bus, when it goes and where it drops you off. It may be the GPS coordinates of your house, the address, or even the roads that you take while going by bike. Depending on the situation, one of these forms of information may be much more useful to you and much more easily comprehensible than the other. When going by bike, for example, the GPS coordinates don't help you that much. So, in the end, all of these forms represent the same information, that is, where your home is. This precise concept is applicable to the sinusoidal waveforms. I will just draw a general sinusoid once more. Let's graph voltage over time. And we have this kind of waveform, which has an amplitude A and is phase shifted up to here with a phase shift phi. Now, these are many points. This is a function in time, but consider for a second if I give you two other diagrams. If I give you a diagram of amplitude over frequency and phase shift over frequency, I'll draw this for you. And I now attempt to represent this sinus function in time in these two coordinate systems. Well, this sinusoid has one frequency. Let's call this frequency f1. And let's imagine it is here on this axis. So it has one amplitude, and this amplitude is A. And let's just put it at the same distance here, A. And what we have is a point in this diagram. And this same sinusoid has a phase shift. The frequency over here is of course the same, frequency f1. And the phase shift here looks like something on the order of 90 degrees. So let's just imagine it is here. We put 90 degrees. And also represent this with a dot. Now if I give you just these two diagrams, you have everything you need to reconstruct the sinus function if you know that you are supposed to reconstruct a sinus function. You have the frequency, you have the amplitude, and you have the phase shift. And that is all you need to represent this information. Last time we discussed how these 2 points of data can even be further contracted into one complex number. Let me graph this in one coordinate system for you. So the frequency axis stays, but since we are now dealing with complex numbers, which are in essence two-dimensional numbers, let's introduce a further axis. So let us here graph the real part of a complex number z, so the real part. Of the complex number z, and the imaginary part on the vertical axis. So, we have the same frequency, f1, and let's put this here. And we discussed last time how to get to this kind of complex representation. And let's just make up some complex number that represents this here. We have a magnitude of A, so it should be this distance of A from this point F here. And it is, for example, over here. So it has some imaginary component and some real component. And you can put it here as Z1. So this number, if you graph it properly, has the same information as these two diagrams. So far, so easy. Now let's consider what happens if we don't just have one sinus function, but we add another. For this exercise, in thought, I will copy this sinusoidal function I have graphed to the left here. And now let us add another sinus function that has a different frequency. So this sinus function has a slightly higher frequency, it has a different phase shift, and it has a slightly smaller amplitude. What happens if we add these sinus functions on top of each other? So we will have something here. It will start here, then it will go down as these two things are added. Then here the function will rise much more to a higher peak. And never mind my limited drawing skills, you will obtain some function that looks perhaps still vaguely resembling of a sinusoid, but it begins to look more complicated. Now imagine what happens if you add a third and a fourth sinusoid. You will obtain increasingly complex summations of these things that cease to look anything like a sinus. This red sinusoidal function that I've added here, I can represent in the same way that I've just shown to you in these coordinate systems. Now let us look at what this looks like in practice. So we have a second frequency, which is slightly higher than the first frequency. So perhaps we have it at this point, f2, here. The amplitude of this signal over here, a2, is slightly lower than the first. So perhaps the point is here. And the phase shift in this case, well, it starts with a downward movement, so it's 180 degrees, so the phase shift is considerably larger. So the phase shift would perhaps be graphed here. And similarly, we can do the same thing, the same contraction, and display these two new points, also as a complex number. And in this case, since the phase shift is 180 degrees, that makes it easy where it lies. We have the frequency of 2, and we go backwards on the real axis, and we have the second complex number located somewhere here. The precise locations of these complex numbers for this example are not important. We've discussed last time how to obtain the precisely correct complex number that represents each of these sinus functions. But what you should notice is that this rather complicated convoluted display contains precisely the same information as this way here, where you just have two complex numbers, or alternatively these two graphs where you have amplitude and frequency, amplitude and phase shift plotted against the frequency. However, these displays are considerably more attractive, let's say, in terms of their simplicity. It turns out that even for signals that you would not recognize as sinusoids, you can find such a display in amplitude and phase shift over frequency by a mathematical transform. So consider this signal. It is in this case a completely arbitrary signal, and you might sometimes encounter this type of signal, but you can nevertheless represent it as a sum of sinusoidal functions. And in this case, the mathematical device that gets us from this difficult time domain representation to some graph over frequency is the Fourier transform, which we will look at in more detail in a second. So let's look at the first mathematical device that we will use to obtain this kind of frequency spectrum, the Fourier transform. We have posited that even signals that look nothing like a sinus function can usually be represented by a sum of different sinus functions. So consider any arbitrary signal. How do we obtain this frequency spectrum? First, let us write down this voltage as an abstract idea of various sinus functions added So last video we've discussed that we can represent a sinus function as e to the j omega t plus phi. And let me write this down. This function here I will call u of t as the time-dependent voltage. And we imagine that we can write this as the amplitude 1 times e to the j, which is the imaginary unit, the first frequency that we use, times t, and the first phase angle. And then we just sum this up. So we have the second frequency, j to 2t, and so on. In reality, this may be a continuous distribution, but for illustration purposes, let's look at it like this. The Fourier transform is defined by the following equation. You have generally denoted as large capital X as a function of the angular frequency omega, the Fourier transform. And this is the integral from minus infinity to plus infinity over the entire time dt. Your function as a function of time, the small letter x of t, multiplied with this slightly ominous term, e to the minus j omega t. This is all the magic that happens for the Fourier transform. If we are concerned with voltage, then we may obviously use the capital U and the small u for this, but this is the general definition. Now let's think about what this function actually does. So what we're doing is we are taking the entire signal, the entire time domain, and we're multiplying this with e to the minus j omega t. The minus in the exponent gives us the information that we're basically dividing by this e to the j omega t. And this e to the j omega t is a generalized sinusoidal function. We've seen last time that we can represent this also in this figure as the cosine plus jade sinus. Let me repeat how we can write this kind of expression here as sinus and cosine functions. So we have e to the j omega t is the cosine of omega t plus j sine omega t. Now what happens if we understand a signal as composed of these different kinds of component frequencies? What we're doing to obtain this spectrum is we apply this formula for each and every omega that we can find, and the result of this term is our value at this angular frequency omega. Now what happens? We have this x of t, which we write as a sum of different frequencies. And now let's consider what happens for each of these frequencies. And let me write this term here for an example frequency. So what happens here in the integral is, for example, we start with a1 times e to the j omega 1t plus phi 1, and we multiply it with this term where we're trying to look for omega here, times e to the minus j omega t. And this is what then stands here, summed of course for different component omegas in our signal. What happens? If we multiply these exponents, what we're essentially doing is adding the exponents for the functions. So we simplify this to a1 times e to the j, copy this term, omega 1t plus phi 1 minus omega t. And in this case, this omega 1, omega 2, omega 3, omega 4 is all the different omegas that may be in your actual function. And omega t is the frequency for which you're trying to calculate the spectrum. And now what happens? In this case, if the omega 1 is different from omega. Then what will result is that this difference, omega 1 minus omega, is finite. It's not zero. What we have here, we further simplified, equal to A1 times J to the omega 1 minus omega times T plus phi 1. So if this difference here is not zero, then we have some time-dependent sinusoid that is a result of this kind of calculation. So for every omega in our x of t that is not the frequency we're looking at, this turns out to be just such a function here. The cosine of some resulting frequency plus j, the sinus of some resulting frequency, and then we integrate over the entire time. Now the magic happens. What happens if we integrate over some kind of sinusoidal wave over the entire time? You see that these areas over and under the curve always cancel out. Over the entire time period, if this difference is finite and we get this kind of shape, this integral turns out to be zero. And that's very convenient. For each and every frequency omega that is not for each and every frequency omega that is in our signal, omega 1, omega 2, omega 3, up until infinity, that is not the omega we're looking at here, this cancels out. But there is one frequency that is exactly equal to the omega we're looking at in the transform. And for this frequency, omega 1, in this omega, in this case, and the omega that we're looking at cancel out. And so this term here becomes zero. And what we end up with is this amplitude. Let me write this here. For the omega n in our function u of t, where the omega we're looking at for the transform equals the omega n in the signal, we get something here that looks like a n times e to the j phi n. And e to the j phi is just, well, that's a complex number. It's not, it's some constant here over time. It doesn't vary with time. And so the integral here will essentially turn out to be not zero. And so the components where the frequency in your signal is exactly the frequency you're looking at with this term here, this will produce some finite result of the integral. And all other frequencies are lost in this kind of multiplication. So this rather lengthy explanation in mathematical terms makes you able to imagine this as if you're looking through the window of omega here in this term at your function, and only the omega that is with the same frequency in your signal is visible to this term. Everything else cancels out. And this is how this transform makes you able to distinguish which frequencies are in your signal and how strong. This is the magic of the Fourier transform. Let me give you, for completeness sake, the way to get back to your original signal x of t. The way back is the inverse Fourier transform. Fortunately, this is much more intuitive than the actual Fourier transform. What we're doing is we're reconstructing a time domain signal from this alternate way of looking at it in terms of the frequencies that are there. And so we have some term, 1 over 2 pi here, which is a concern regarding the power density of the spectrum, which should not concern us at this point. And we integrate from minus infinity to positive infinity over all our frequency components. And we multiply them with the sinusoidal function again. And so we take our amplitude density spectrum and multiply it with the sinusoidal function, and we end up with our time domain signal. Now, two things to clarify. When explaining this just a second ago, we imagined this time domain signal as composed as of a sum of distinct frequencies. In reality, it is of course a continuum of frequencies, not single dots. And this continuum may look something like this, and it is actually a density spectrum. This is a finer technical point. Another point you really must consider when using these kinds of transforms is whether they actually exist in mathematical terms. For them to exist, this integral here must be finite. And now let's look at what actually happens when we try to form this kind of integral for a sinus function, which we have been considering all along. We plot here x of t over the time t. And what you see is, if you integrate from minus infinity to plus positive infinity, this integral continuously oscillates. It never approaches a finite value, and that's a problem. So this transform for even a sinus function curiously does not exist. This is something of a cruel irony of this transform. However, we have lots of functions, for example the sinus function, that we would really like to be able to look at in this way and handle. This includes the sinus function, or for example a step function. Which is just the jump of a function from 0 to 1 at time 0, and other such functions. And the problem that you spot here is that this integral only really converges when this function itself, x of t, is converging. Now, how do we solve this? We could think about modifying this term somehow so that the integral converges more often. Let's think about this. We integrate our time domain function, and we want to still see what kind of frequencies are in there, so we can't really skip this term. But what we really can do now is we can multiply it with yet another function that makes this, that compresses this term in such a way that it really converges for most cases. And you can imagine it like this. If we use an exponential term, an exponential decaying term, it would look something like this. This is the exponential term, and it creates some boundaries within which, for example, the sinus function would now have to operate when we multiply. And what this means is we multiply this with some term e to the minus sigma t, and the resulting sinus function from this multiplication turns out to be within these boundaries. Well, let's plot it with the correct frequency. And it will look something like this. It is this same sinus function, just that now it converges on 0. Similarly, the step function is now compressed by this e to the minus sigma t term towards 0. And now, if we constrain ourselves to signals that start at time 0, not minus infinity, and we copy this dt because we integrate over time, we end up with the Laplace transform. And the Laplace transform now converges for many of these cases and actually exists and is therefore much more useful to us. It is the Laplace transform here. And we call this domain the S domain. We reach now a transformed quantity, x of s, no longer x of just omega, because we've added this minus sigma term. Where this s comes from, I will show you in just a second. And what we now do is we no longer transform the signals strictly into the frequency domain, but in something called the S domain. And these two terms that we have now multiplied with each other, we can just mathematically simplify. So if we multiply the exponents, well, the exponential functions, we add the exponents. And now let's contract this. We keep the e, and we have the t in both of these exponents. So we keep the t here. And we still have the minus sign in both. We have the j omega here. And we keep the sigma. And this entire term here, we rename S. And this is why we're now transforming into the S domain. What we've essentially done is we've made our transform much more useful for us in the general case, and we have added a decaying exponential term which forces this integral to converge in many, many cases. And now suddenly these transforms are possible for most of the functions that interest us. This transform has other interesting properties. For example, it is a linear transform. Also, it does something very interesting to the first derivative of a function, or indeed multiple derivatives of functions. So if you, into this equation here, plug the first derivative of a function, what you get is the following. If you denote that you Laplace transform an operator, we use this stylized L of a function, and we will now want to transform df by dt. And this turns out to be just s times the Laplace transform of the original function, which we call, in this case, here we had used x of t and x of s, here we use f von t and capital F of s, minus some initial conditions, which we will skip now and call them 0. What this does is it enables us something that we hadn't considered so far. It enables us to write differential equations as essentially algebraic terms. And this will come in handy in just a second when we come back to describing our electrochemical signals with electrotechnical circuit elements and how they interact with each other. Now, what we've mainly looked at so far is how to display or analyze signals. But what we really would like to describe is our electrochemical system. A system in general, I will define here as something that transforms an input into an output signal. Let me write this down. We have an input, which goes into our system, and we receive some output. The input I will call here x of t, and the output y of t. And the system might, for example, be something like a capacitor. In general, a useful way to describe a system is by its impulse response, because it contains all the information necessary to fully describe the system. I will show you how to get from the input signal to the output signal using the impulse response in a second. What we've done so far is look a lot at the Laplace transform. The Laplace transform can be applied to certain system descriptions under some conditions, and the conditions are that the system must be a linear time-invariant system. Also sometimes abbreviated conveniently as LTI system. Now let's look at what this means in practice by transforming the input into the output. Imagine what your system does is, for example, a pendulum, and you give the pendulum a push and it responds in some way by movement. Now let's plot the input. At time 0, for example, you give it some push. And what you get from the system as a response is its impulse response. You give it an impulse and you get a response, which is the output. And the response to this may, for example, take this form. Now, a linear time-invariant system means that if we put in twice the impulse, so if we hit it twice as hard, we get twice the magnitude of the response. Time-invariant means that if we hit it, for example, in an hour or in a day, with the same impulse, we still get the same response just in an hour or in a day. Now, what does that mean if we give our system another push, maybe here, and it's half as strong? What happens? We get a response that looks like this, but it's also half as strong. And if we give it a third push at an even later time, with the original strength, we get another response that looks like this and also has the original strength. And what we have as output over time is the sum of all the responses of the pushes we've given it. And this is just these three impulse responses summed up. So here we only have the first impulse response active, and now we add the second one, and here we reach the third. And we get this kind of summed up response. In reality, we usually don't just push our system, but we excite it with a continuous signal. If we imagine this continuous signal as ever closer pushes, then we get from this kind of discrete calculation to the so-called convolution integral, which we have plotted here. The convolution integral is just the impulse response multiplied with the input function at all the times that happened before the actual time you're looking at. And if this kind of integral looks extremely complicated to you and difficult to solve, that is because it is. If the system is even moderately complicated, this will turn out to be very difficult to solve. Sometimes it may even be impossible. However, we've introduced the Laplace transform, and for a linear time-invariant system, the Laplace transform can be applied to a system. And this turns this complicated integral into the multiplication of the Laplace transforms of the input signal and the impulse response. Now let's move to the Laplace transform in this kind of description of our system. If we Laplace transform this kind of description, we have still an input, which is now the Laplace transform of x of t. And this is nothing but x of s, because we've moved into the s domain. We have our system, and we will call this Laplace transformed input impulse response G of S. And the output is also Laplace transformed into Y of S. And here we call this G of S transfer function because it is what transfers the input to the output signal in the Laplace domain. What this means, because of this property that it's just multiplication, is that we can express our system property that characterizes our system in the Laplace domain as the quotient of output over input. And this kind of structure should be familiar to you, because we've been using this kind of fraction to describe what our voltage is, for example, in response to a current excitation. And that is our impedance. So if we look at the capacitor and do this exact same process, we will receive something that is U over S, the Laplace transformed voltage, divided by the Laplace transformed current. And we call this the impedance Z. But now we have the means to calculate what this impedance in the S domain actually is. And to do this, what we do is we Laplace transform the characteristic equation of the capacitor. Let us write this down. In the time domain, we have the capacitive current, IC of t, is equal to the capacitance times the rate of change of the voltage. Now this is a simple differential equation, but if we Laplace transform it, differentiation turns into the multiplication of the Laplace transform of the original function with S. And these are the initial conditions. And for example, if we assume that our capacitor is initially not charged, then this turns out to be 0 and just goes away, which is awfully convenient. Now let's Laplace transform this equation. We receive here on the left side just the Laplace transformed current, which is now capital I of the capacitor as a function of S. The constant C Laplace transformed stays a constant. And this, the rate of change of the voltage, turns into the multiplication with S of the Laplace transform of the voltage of the capacitor. And now we can calculate this quotient, U of S over I of S, very simply. And we get the impedance of the capacitor, which I will call Z of C, as UC over IC, both as a function of S. And for this we just rearrange this equation and we receive 1 over SC. And if you remember, this S, when we introduced it in the Laplace transform, just remember this here, is equal to a sigma plus j omega. And the sigma represented the exponential term, the exponential decay term, and the j omega the sinusoidal term. And if we just look at this signal for the frequencies where we have no exponential decay or anything, so we assume that sigma equals 0, then we can define that S equals j omega if sigma equals 0. And then this equation turns into 1 over j omega c, which is the frequency domain representation that you're familiar with, except now you know how we got here. And this is how the Laplace transform helps you describe, in simple terms, your system.